studies. So, Silva, please take over.
Yes. Okay. Yes. So, hello everybody. So I will continue what I have presented yesterday on experimental studies, and today I will go more on internal gravity waves and the different techniques for internal gravity waves and for mixing. I will just start. Yesterday I showed there was a movie, and I ended my talk with this movie. I will just start from this point in rotating stratified fluid. And what I said yesterday is this equilibrium is due to the fact that stratification restore vertical motion. And this is you have seen this equation yesterday, plus n squared z is equal to 0. And this is when you have stratification, I recall n is the buoyancy frequency. If you have now rotation, preserves, restore, so the rotation is the Coriolis force that will restore horizontal motion. So it's possible using the same, using similar thing that yesterday for the first equation, this one. You, by conservation of angular momentum, you can have an equation for the velocity, the radial position as a function of dt squared, plus term which is related to f, and it was a term that is minus f squared delta r, which is equal to 0. F is equal to 2 omega. Omega is the rotation rate of the ambient fluid. So that's what you observe for the pancake is just a result of these two equations. In fact, what you can do is write the pressure anomaly inside the vortex, and you have two equations. So we'll work on pressure anomaly between the vortex and between the pancake and the outside, pancake and the ambient fluid. And when you're at equilibrium, you have two equations. One is dp over dz, which is minus n squared times z. This is a result of the stratification, and this is the fact that you have vertical motion that are restored by the stratification. You have the same for the rotation rate times r. So I will go omega m. Omega m here means that you have a rotation rate of the pancake, which is not exactly equal to the rotation of the ambient fluid. That's why you have a omega m, and this is why you have Coriolis force. And if you integrate both, you have this equation, rho naught f omega m r squared over 2 plus rho naught n squared z squared over 2. And so that's just the results of the consideration between stratification and rotation and looking at the hydrostatic pressure, and what you obtain is an ellipsoid, which is what is observed experimentally, and with the aspect ratio alpha, which is h/d, meaning that you have a pancake, which is like that. H is this, d is this direction, and you can, it's easy looking at the previous equation. This is, of course, a constant. It's the integration constant. And you have these results. And it's also a very good approximation, a very good agreement with the experimental results that I have shown in the movie. So knowing the stratification, F, omega m, you have, you can calculate alpha and you get very nice results as a comparison with experiments. And this is due to the fact that the stratification will play as a restoring force, and it's similar for the Coriolis force. And in fact, this is these two restoring force who will be the reason why you have propagation of waves in a stratified fluid, which are called internal waves. And I think you have also saw yesterday that you have also inertial waves due to Coriolis force, and they are very similar. And when you have both, you have a competition between Coriolis force and stratified flows. Both allow the propagation of waves. They don't have exactly the same dispersion relation, but they are very similar. And you have to take into account both in reality. That was just a short reminder from yesterday, and saying that we can go a bit further in the description of the experiments, and with good agreement with the theory. Now, the thing I want to discuss more in details today is the something about internal gravity waves that you have that will propagate in stratified fluid, and I will discuss. I have decided to present the internal gravity wave in the context of an attractor, a linear internal gravity wave attractor. So that's something in particular. So you don't have attractor everywhere, and I will explain why I call this why it is an attractor. But I think I can present a lot of things, of experiments in this study. Just to mention, there has been a lot of work on this study by Leo Maas from the Netherlands, Evgeny Hermaniuk from Novosibirsk, Stuart Dalzel from the Kingdom, and Thierry, myself, in Lyon. And we have spent a lot of time studying these attractors and many properties with this attractor. There were 2 PhD studies, 3 PhD studies on this attractors. So I will go step by step on linear internal wave attractor. So I will just start with a short movie about an oscillating object. So I think you have already seen this movie or a similar movie yesterday. This one. So it was the movie when we stratified the fluid with the double bucket method yesterday, and now we have an oscillating object, which is this one. It's oscillating at a frequency omega, and And what you see now is that when it's oscillating at frequency omega, you can see 4 directions of the propagation of the wave. This and you can then specify an angle theta for the propagation of this wave. And this angle, that you can see here, theta, is linked to the frequency omega and the stratification, which is quantified by the buoyancy frequency n. A small thing that in this system, which is a very interesting system, is that this angle theta with the vertical, so you have this, you have vertical theta. This direction is the direction of the group velocity, is the direction of energy. In the dispersion relation that you have seen, omega equal n sine theta, theta means the direction between the vertical and the phase velocity, and in internal wave, phase velocity and group velocity are orthogonal. And when I write here with this direction, you have a cosine. It's just a matter of the direction. So if I go back this, what you see is that if you have an oscillating object at a frequency omega, you have 4 directions. This direction are the direction of the group velocity, and I use omega equal n sine theta. So in the movie, it was written cos theta, but it's not the same angle here. When you look at the group velocity and you have a sine, is the angle with the horizontal. And that's important. And the phase velocity is this one, the phase velocity in the internal wave, which is proportional to the wave vector k. And in this case, theta is the direction of the phase velocity with the vertical, with the direction of gravity. And that's what you observe by the oscillating object, that the most classical picture you can see, and this cross that is very famous for internal gravity waves. If I just come back to the movie, this one, to this movie, what you see is that the motion you see are just because you have a motion, you have the motion of the wave field, but you see that some perturbation when you look through the tank, and this is because you have variation of the index of refraction. And I will come back to this a bit later in this lecture. And it was here a visualization with a technique that is called ombroscopy. And you can see this because n is inhomogeneous in the tank. So n means the index of refraction. Okay, and when you have this, you can see through the tank, and it will be related to the density. And this movie has shown in particular the dispersion relation that you have here. You can have, which is similar to this movie. I put it some colors to indicate the velocity field. Okay, not working. And what you can see here is the 4 directions given by the angle theta. This is the group velocity, or the velocity of the energy propagated. This direction, the phase velocity is going in this direction. And this will give you the famous shape, the cross shape of the internal waves. The other part that is really important in this dispersion relation, there is no wavelengths. No wavelengths in this dispersion relation, meaning that it's the boundary conditions which will impose lambda. And this is that is a very important point. So you have seen this yesterday, and you have a talk on a lecture on internal waves, and this is just some reminder for the follow. The second part that is important of internal wave and that I want to discuss in two, let's start with this one, was just a reminder, into its internal wave reflection. Maybe Thierry said some word on internal wave reflection this morning. I will just recall what happens. So we look at the reflection of internal waves on the slope. So when you have internal wave on the slope, which is so this, with an angle alpha, your wave, I do it properly, you have a wave that's coming this one, with an angle theta. So if you do the classic, so that's with the vertical, it's theta, which is fixed by the dispersion relation. If you are in optics or in many directions, you want it to have like the Snell-Descartes relation, this one. This is not the good one. So the reflection is different than the classical reflection. What you want to, what is constant, theta, the angle theta is constant, is conserved. And the angle theta is conserved during a reflection, means that the reflected wave will have an angle theta and will give you this direction. And this is this one that is the reflection of an internal wave. That's the basic feature, and you have a reflection of internal wave that will you need to keep this angle theta, and then you will play with a geometry. So that's just geometry, just sketch. I will then discuss what happened in a closed domain. Okay, the closed domain, more precisely, it's a trapezoidal domain. I will explain the reason just in a minute. So basically, the domain you're considering is this one. So you have 3 walls, this one, and this one. There are 2 walls that are horizontal, 1 wall that is vertical. Here, reflection and vertical or horizontal will not change anything as the Descartes relation. You just take this picture, and when it's this, you have a wave doing this one. You have the reflection that is this one. And it's like Snell-Descartes, like in optics. But in this domain, you have an inclined slope. In the experiments of the attractor, we inject energy over the whole height here. And I think the best is I show you a movie. The movie is this one. So basically what you have is you have a wall, that's the wave maker. This wave maker will oscillate, you will see in a minute, with a small amplitude and frequencies, which is of the order of 15 seconds, which gives you a value of omega over n. This is a tank that is 1 meter in height. It's 2 meters in this direction. It's few centimeters in thickness, meaning that you will have a quasi-2D experiments. It's mainly what we do in the lab. We often study only 2D system. What is possible, and now you have this slope that I have just presented. The line you see here, so it's a way we made the system. So we have a stratified fluid, and then we put a grid with some dye at different location. We move the grid into that direction, and we move out the grid, and we have these lines, which represents line of same density. And when you will have motion of the internal waves, you will see some motion of this wave. Now I start the movie. You can see some oscillation in this direction. You see motion of this almost everywhere. And you see that there is a shape where there is motion is larger, which is this one. You can see that you have energy that is concentrated in this pattern. Of course, this pattern is not completely strange. This angle, as I said before, we look at the angle of this direction, which is the direction of the energy, with horizontal to have theta with omega equal n sine theta. And you have this nice pattern, and energy is concentrated along these patterns in this time. What's important that you inject energy for the whole height, and the energy that is injecting here, everywhere in the tank, that is injecting on one side of the tank, is localized in this pattern after a few periods. If you do the same, but with a different frequency, we have exactly the same system. We change the period, so we change omega. And if you change omega, you can also see there is a shape, which is this one. We'll start again. If you look carefully, it's almost, this one is more in this direction, but it's, you have also a pattern that is obtained after a few forcing periods. And that's something that is peculiar because you have this trapezoidal geometry, but it's not the chance. We change the value of omega, we have many values of omega, and we always have a pattern. The pattern is always a bit different because this direction is fixed by theta, and theta is still related to omega over n. But when you impose omega, n is fixed by the stratification you have created, you can obtain such pattern. And the question I want to address is that, can we explain the shape of this pattern? Can we explain why we have this kind of pattern? So if I come back here, what you can see is that after few forcing periods, energy is localized on is concentrated. We have more there. We observe a concentration of energy on a closed loop. This is the pattern I've shown you. And this closed loop is called internal wave aspect. And it has some properties that are very interesting in an experimental and theoretical point of view. Just if I do it, this is typically a pattern which is like that with theta, so just defined. The other thing that is very important is that you have a transfer of energy from large scale which is the scale of the injection, to smaller scale, because the energy is concentrated on an attractor, and the thickness of the attractor is much smaller than the injection scale, which is the whole height of the domain. And this transfer, it's only linear. It's only because of geometry. But I will just. So the question is, how can we interpret this result? If you have any question, don't hesitate to ask them on the chat, or if there is some question on YouTube, I will ask. I will have the question. So to interpret these results, I go back to internal wave reflection. That's a good question, and it's I will answer this later in my lecture. It's the question I will address and try to explain experimentally what is the smaller scale here. Smaller scale here, just if I come back to the movie here. So you have the injection here. It's this height. On the small scale is that you have motion that is localized in this thickness. And I will explain why we have a smaller scale, which is related to this thickness.
Sir, I have a small question.
Yes.
Sir, how do you see this, like the transfer of energy, like when you are giving a, when there is a source on the left side,
Yes.
and there are, if we see it as two beams propagating, one upwards and downward, and after reflecting, do they accumulate energy on the right side on that wall, or do you see it as a continuous reflection?
I will also come back. what you see that you have reflection, 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 and you have always the same shape. It's a closed loop. This one. I inject energy everywhere, so means that you have an internal wave starting from this point, this point, this point, this point, this point. So you have every point of the wave maker will generate a wave beam. And you look at the movie, when you look at what happens at the end, all energy are localized in this pattern here. But you have also motion. You have wave here. That's why you have some motion, but very, very small motion here. So the energy is much more visible here after some reflection. I will show you the construction reaching to this pattern later. There is no mixing for the time of observation because the amplitude is very, very small. And with a small amplitude, you don't see any overturning, meaning that the density is stays smaller, so you don't have inversion of density. So large density over small density, which will lead to mixing. You don't have this here because it's small motion. The amplitude of the perturbation, I will explain how is it set and fixed in experiments in a few minutes. I will come back to this question. One thing that will set the perturbation is the internal wave reflection. So I will redraw again the reflection. You have an angle alpha. You start wave that is this one. So again with the vertical theta, we go again this way. So this is also theta. Now you have a second wave. You have a wave beam. Basically, this distance is the wavelength of the incident wave. And if you do the same, you have this. And this is the wavelength lambda of the reflected wave. What you can see in this just geometrical shape is that lambda of the reflected wave is smaller than the wavelength of the incident wave. So just by reflection, and it's just geometry, you have transfer of energy from large scale, which is given by lambda, to smaller scale, which is the reflected wave. And this is why we have made this shape before. It was to have transfer to small scale once, it comes back, another transfer to smaller scale, it comes back, another transfer to smaller scale. So just we put, by this closed domain, we have many reflection on the slope and many transfer to smaller scale. So that's one part of the trapezoidal domain. Domain has been chosen to have many reflection on the slope. So we have this transfer energy transfer to smaller scale at each reflection. just to give you, that's a calculation, is just geometry. You have this relation, and this is sine theta minus alpha divided by sine theta plus alpha. It's just geometry in this plot, which gives you this coefficient, which is smaller than 1. And at each reflection, you divide the length, the wavelength by gamma. So after n reflection, your wavelength is divided by gamma to the power n. Lambda r is proportional to gamma n lambda 0. So that's just a way to transfer energy from large scale, which the initial length scale was lambda naught, and lambda naught, it was, the injection was a mode 1, and the mode 1 has a very large wavelength. And after, sometimes it's much smaller. This is totally true. The oscillation decays at different rates in the different parts of the tank. It really depends. And the decay is related to the finite width of the tank, and I will explain. Not to make too many, to wait too long. It's because of viscosity, and viscosity will don't play the same role everywhere in the tank. So that's why you have a decay that is different everywhere. Basically, you see energy on this pattern much longer than, for example, in the center. Okay, so it's just what I have explained is just at each reflection what happens. When you have a closed domain, you have many reflections. And now, why do we have this pattern? That's called an internal wave B. So, to explain, the wavelength will decrease permanently at each reflection if there is no viscosity. If there is viscosity, and that's the main mechanism that we have to be taken into account in the lab experiments, is because of viscosity that will restrict mechanism. And I will do more quantitative analysis of this parameter in this lecture. But that's the crucial parameter that has been to be taken into account, is the viscosity. First, I will just explain the transfer mechanism to smaller scale, and I will come back to the viscosity later. So, to explain this, I will show you this this image. This image is what is called an internal wave bed. So, what we do here is we look at what I will do. So, sorry, put this here. An internal wave beer, we just do a ray tracing. So, it's like system, you look at a particle that's starting from here, you impose the direction of the motion. This is the direction of the energy. Then you look at the condition of reflection. This is here due to the dispersion relation. Again, on the slope, you still have the same angle theta. And you continue the motion with this one, and if you continue, at the end, you end on this pattern, which is, if you look at the direction of the energy, you have this direction, and it's a focalization mechanism when you have in this direction. So at the end, you have this, and if you continue theoretically, you can continue forever, and it's permanently decreasing if you have no restriction, and you will end up to an infinitely small thickness. This is for the wave beam taken at one point of the wave maker. If you do the same ray tracing for another point and going into another direction, still you have the angle theta, and you play exactly the same game. You do this ray tracing. Yeah, I try to follow. At the end, you end on the same, exactly the same pattern as the ray tracing on the left. So you have exactly the same pattern. And you can play this game for every point in the domain. Every point in the domain, and you look at the wave beam and you do a ray tracing starting from this point. Every point of the domain has an internal wave beam starting from this point will end on this pattern. Exactly the same pattern for every point in the domain. Same pattern for every point in the domain, and every direction of the internal wave beam. So just before I will answer this question, if you change the frequency, you have this. You can have the second one I've shown you before, and you also have a nice pattern when changing the frequency. Okay. You have this. So it's what you obtain. You can plan for all omega, all value of n. I will not put it here, but there are many points, and there are a continuous range of frequencies who will lead to an attractor which has this shape. Another range of frequency will lead to this shape, and there are some frequency where there is no convergence, and you have wave everywhere in the tank. And one that is very peculiar, you have an attractor that is this diagonal, another one is this diagonal, and you have many other possibilities. But you have ranges of frequency where these attractors are visible, and this is why we can observe it experimentally. If it's only a single point, it's always difficult to see it in experiments. But since there are many possibilities to see this attractor, when you have an internal wave attractor, every point in the domain will lead to the same attractor. It's just a competition between geometry, this geometry. So it depends on this angle, this direction, and the frequencies. And you can have a map in 2D explaining on which attractor you will end or if you will not end on an attractor. And it was the study by Leo Mars in 1995. Okay. And this is, you have a range of frequency for the, and it is visible. It happens for different range of frequencies, and this is why the frequency. This is why we can see it. It experimented. And this is why it's not a chance in experiments, and this is not a complicated system to see an attractor at the end. When you know n, when you know the geometry, you know which omega you have to choose to get this attractor. Of course, then it's theoretically, it's infinitely small width. In reality, in laboratory experiments, viscosity cannot be neglected. And that's a very, very important result. And really, when you do experiments, you always have to take care of viscosity, and that's the main difference between laboratory experiments and, for example, internal wave in oceanography. You can rescale many things. Viscosity, you cannot rescale it, and it will just change the results you obtain. And when you want to compare to oceanography, you have to discuss the role of viscosity in your lab experiment, that it does not play the same role in a real system, in oceanography, for example. So just have a question, is there an analogous of the Schrödinger mechanisms? I'm not sure I understand the question. Why do you mean by Schrödinger mechanism?
Sangeet,
not sure.
you can unmute yourself and speak if it's possible.
Yes.
Yeah, it's basically when the surface gravity waves are approaching the coastal region, the depth of the fluid becomes lesser, so that the amplitude of the waves is getting larger. Is there any analogous to that particular phenomena to the internal gravity waves, but especially in this trapezoidal geometry? That's what I meant.
Corner are always a problem. Usually we don't really see the corner in the lab because the wavelength is larger, and what happens in the corner cannot be seen. I am not sure there's some analogous mechanism for internal wave. In laboratory experiments, viscosity will play a role much earlier. So In laboratory experiments, I don't see a similar mechanism for internal gravity waves. Corner may sometimes generate waves, but no, I don't think so. Maybe in theory, when you have an angle like that, you may have some other things to take into account, but in experiments, I don't think so. Okay, and especially because of this viscosity. So what happens in the corner is very small, so it's dissipated. Okay, so now that I have discussed that we can observe this wave and we can observe this attractor, I said that you have a transfer of energy to large scale to smaller scale. Now let's see, I just told you that what will limit the scale is viscosity. I want to discuss it more quantitative. And this is what I want to discuss now is how we can do more quantitative analysis of what we observe. I've seen in this movie with the line that we can say few things, but it's just an observation and a comparison with it. I want to go in more details in the analysis, and I will just present different techniques which help for the understanding. And the first one, for the quantitative analysis, we want to measure more precisely the amplitude of the wave, the wavelengths, etc. And as I mentioned before, we have variation of the optical index of refraction, and this will lead to the first technique I want to explain, which is called synthetic shear. This is a very important technique because it's a very easy one to implement in experiments and will give you some answers and some quantitative results. Just know if you want to reference, you have this reference, Strat, that is 2000. To explain what this technique means, I think the best is to show you a movie. Again, you recognize the same system, that the trapezoidal domain. The previous system was nice to see some dye, but it's not easy to implement. This one, you just put a grid of randomly spaced points behind the tank, and you look through the tank. So for the moment, you don't really see a lot of things, but you look at the point with the camera, and these points are behind the tank. Okay, so you don't really see a lot of things. I will just zoom at one particular point, and when the wave is propagating, you can see that there are some variation here of the position of the points. And it's what we will look at with synthetic shearing. And this motion of the points are due to the variation of index of refraction. So I will do this. So when you have this, you can see motion of the dotted points that are behind the tank. And we, I think to explain how these dotted points are related, to any quantity in the tank, I will present this sketch of the experimental setup. So basically, it's this optical system. You have this is the sketch of the experimental setup. And if you have a gradient of index of refraction in the tank, and you have this gradient of index of refraction, when you look with the camera here, and this is the CCD sensor of the camera, you have the ray is bent because of this gradient of density of index of refraction. So this alpha z is related to the value of the gradient m. And this is something that relation alpha z is proportional to dn over d. That's a relation in optics for inhomogeneous medium with inhomogeneous refractive index. I just have a question. I will finish this and I will answer to this question later. So then with the camera, you have a motion delta z, and it's what you have seen in the movie. And delta z is just an optical construction, is related to this angle alpha z, f, which is the focal of the camera, and some distance. To get this results, you just do some geometry with small angle. So if you measure delta z, you have a measure of alpha z. And if you have a measure of alpha z, you have a measure of this gradient of index of refraction. And in the in experiments, what you have is that dn over dz can be related to dn over d rho, which is the gradient of density, and this value is roughly constant Therefore, by measuring delta z, you can measure 0 dz. So delta z is proportional so you have a measurement of the density gradient. So that's the first approach you can have. By using in the camera, you can have access by measuring this displacement to geodesy. The advantage of using random dots, you improve, if you have only dot, you have a spatial resolution which is linked to the spatial distance between points. When you have random dots, it's like in PIV, you can reduce this resolution. You don't have a characteristic size, which is due to the characteristic size of your dots in your system, in your background. So that's why we always use random dots, and we use an algorithm to recognize some pattern that is randomly distributed, and this will help a lot for the resolution we can achieve in this way. And we use exactly same post-processing that we use in PIV. Yes, exactly. It's a multipassing method by autocorrelation. It's exactly the same. And this will help for reducing the errors and having more accuracy. If you do this for the internal wave system that I've shown you, this is for different frequencies, you can see this result. Okay. Okay, we have this. Okay. Okay. Yes, that's results obtained for the internal wave attractor for different frequencies. And you can see this nice pattern that I have shown you before. And you can also see the small size here. To answer the previous question, if the wave maker is arranged in this direction, exactly, yes. Yes, if you have oscillation here, you will end with the same pattern if you have the same angle. And there are, for example, there are people who do numerical simulations that have been done, for example, by Benjamin Favier in Marseille. And he played more with inertial wave, but it's similar. Instead of having a single slope, he has a cube, so 4 slope, and it has an oscillation in volume. So every point are excited, and you have the same pattern at the end. So you can excite what points. So if you have a curved slope, you can also have attractor. When you have a curved slope, you have to look at the local slope, and it's more complicated to do the ray tracing, but you can also have attractor. You have a nice sketch in one of the paper by Leo Mas with I think just to show you a slope that is a double mountain like that, you can have something which is very, very badly sketched. but you have this. Some things. And you have this sketch in one of the paper by Leo Mas. Of course, what I've told you before, it really depends on the local slope. So you have to take into account the fact that you have a different slope everywhere. It's possible. It's more complicated to do it by a simple ray tracing. That's why we use this check, but it's possible. Okay, so you can get these results. As I said, and it was a question, it's an autocorrelation method. And basically what you measure, to be more precise, it's 0 over dx at a time t minus. So to be careful in this realization, so in experiments, to explain, sorry, to Z, what you want to do here, you start the experiments with no wave. That's the initial. Then you start the wave, and after some time you look at the position. Therefore, by having the difference, you have only the stratification, the modification due to wave. So this is a way to measure the perturbation due to the internal gravity waves, internal waves. And it's also, when you do an experiment, what I said is that you look exactly what happened in the tank. So you want no motion everywhere, no motion of the air, no motion, no modification of the position of the tank. So that's why we do this method, which helps a lot to have this motion due to the presence of internal waves. And this technique, this is possible in 2D. 2D is because you are looking through the tank. So you need 2D, or if you have some symmetries in your system. If you don't have this 3D motion, you cannot capture it with this technique. And also no mixing. If you have mixing, you have strong variation of n, and you cannot relate the variation of n to the variation of the density. So you don't need to do it for too long time. And this is why you do this method. No waves at t equals 0, and at t waves. That's why you do this difference. And the final comment is that synthetic Schlieren is very, very interesting if you look at small scale, because since you look at the gradient of density, you increase the visualization of small scales because you have this derivation compared to the density, for example. When you do the derivation, you multiply by k, so you divide by lambda, so you increase the visualization of small scales compared to a large scale. So that's why it's an interesting technique. Technique for visualization of small scales. And this is because we are looking at the gradient of density, which is proportional to k times the density So you increase the small scales by this method. And to answer this question, I will answer this question in the next part. So about the energy. So what I've shown you is that synthetic lines are very interesting and give you already interesting results. You have seen that you have this thickness that is really visible in this technique, and the thickness. So you have a competition for the attractor between focalization, that's the energy, and viscosity, and viscosity it's the dissipation. And looking at the Navier-Stokes equation, the dissipation is stronger at small scales. And small scales will dissipate more than large scale. And this is what will limit the dissipation and why the thickness will be finite. It's due to the viscosity. And this is what I want to talk about in the next part, is that could we explain quantitatively more this competition with an energetic approach. An energetic approach means that at the end, you have a steady state. Steady state means that if you look at you can write it this way, D equals 0. Just to explain what I have just written, that the variation of the energy of the whole system, that the injected energy, and that's the dissipation. If you have a finite set, what you inject is dissipated. So the energy cannot increase at the end, because at each time the injected energy is compensated by the energy that is dissipated because of the viscosity. So, and this is what we want to check in the experiment. We know that we inject energy with the wave maker. We have the dissipation due to the viscosity. Do we have this balance? So we have a balance between injected energy, injected power, and dissipated rate. And I think this, answering the last question, the pumped energy is just dissipated at smaller scale. It's too small to increase the temperature. We cannot measure it. But this dissipated energy. Yes, you have some. You have also walls, so it may various, but it's very, very small, this dissipation. Okay, so if you have this balance, just to explain, experimentally, we wanted to measure these two quantities. The injected power is just related to the velocity on the times the pressure. So this is the energy that is injected over the wave maker, and the dissipation, you have a minus sign here, is due to the viscosity in the volume. The gradient of velocity squared. So we have the dissipation is due to the gradient of velocity and the viscosity, which is the dissipation. This is the injected power. So to quantify these two quantities, what we need to measure is this quantity is the velocity. So the synthetic Schleben cannot help if we want to quantify this quantity. It's possible, but we need to have many calculations, and you will have not a good accuracy. So to estimate these two quantities, we measure directly the velocity field. And more precisely, what we do in experiments, we have a laser sheet. So this is done using particle image velocimetry. So you may know this technique. I will just explain how it's performed in stratified fluid. So particle image velocimetry, the fluid is seeded with particles, with light reflecting particles. The particles are usually very small, so typically we use particles of size of few microns. So in fluid mechanics, we try that these particles have their density equal to the density of the fluid. Of course, for stratified fluid, it's not possible except at one height. So we use that are slightly denser than the system. I said this is a typical particles we used in ion, meaning that the density of the particle is larger than the density of the fluid in all depths. If you do that, of course, the particle will settle. So if you put the particles and you wait many days, all the particles are at the bottom. So when you put the particles, you need to do experiments just after putting this particle. Basically, the settling velocities of these particles Vs, it's around 8 to the minus 5 meter per second. So you, if you have 30 centimeters, you can calculate you need long time to have this setting. So the density and the size of particles are small. The size is small. The density is close to the density of water, so that the settling velocity is very small. So that also the velocity of the internal waves is larger than the settling velocities in Vs. That's the first thing. And there are also an important thing to check is the Stokes number. Stokes number is this quantity. It's rho p squared by 18 mu of the fluid, the dynamical viscosity. And this is a characteristic width, a characteristic velocity of the fluid. And this is a characteristic scale of the fluid flow. Basically, this is the characteristic time of a particle this is just to explain over the characteristic time of the flow. And what we have in all our experiments, Stokes much smaller than 1. And when you have this, particles follow the streamlines. So by measuring the motion of the particles, we can obtain motion of the flow. We can have the velocity of the flow. And that's an easy technique. And then we use cross-correlation algorithm to get the velocity of the flow by looking at a camera. So the experimental setup using such technique is this one. You have the fluid. You have randomly distributed particles. Distributed particles. Then you have a laser sheet. In the midplane, usually of the tank. The midplane of the tank, we can do, if you have sweepy tank, we can do horizontal motion, vertical motion. It depends where you have your laser sheet. And you measure the intensity with a camera. We take an image of the light pattern emitted by the particles. Or recorded with a camera. And when you compare two successive images, you get an estimation of the displacement of the light pattern, which is an estimation of the 2D velocity in a 2D plane. It is estimation of the displacement of the light pattern, and this gives you an estimation of the 2D velocity in a 2D plane. So basically, if I have, this is vertical, horizontal, transverse direction, you can measure the x, z in the midplane, and the same for the vertical velocity. And that's the classical PIV experiment that can be measurements that we can apply for internal gravity waves. Now, going back to my internal wave attractor, you have this. This is the results that we can obtain from this experimental technique. So in this you have x, you have the position, vertical position, you still have the slope, and here I compute the amplitude of the velocity field. U is the horizontal velocity, W the vertical velocity. White, there is no, the velocity is very small, and the color is this amplitude, and the different arrows are the direction of the local velocity, So you can see, as a function of time, that you have this localization of energy over this pattern, and the energy is strongest in this branch, which is just the branch after the reflection on the slope, which is the branch after focalization. And in this way, using this technique, we have a nice estimate of the kinetic energy, which is what is basically shown in these short movies. And so in this, I will do this. This is how we have an so the energy measure, so the kinetic energy measured using PIV is localized on the attractor. And it's what is shown in this short movies. So as I told you before, I wanted to discuss the energetic approach. So I discussed that we have injected power, we have dissipated. With this technique, in a recent paper, I will not go in long details. It's a paper by Geraldine Davis in 2019. We have been able to, from the measured velocity field V that is measured, we have been able to estimate the injected power, the dissipated one. In fact, from the measured velocity field, we can estimate the pressure using linear Navier-Stokes equation, and then calculate the injected power. We can estimate also the dissipated rate. And I will just show you this comparison, which was what was obtained experimentally. So you can see, so it's averaged over the forcing period. This is D. This is the injected one. And you can see that from the experiments, we have a nice agreement at when the injected power is small. It's where we have everything is linear and we have good estimate. Of course, we cannot estimate all the dissipation term. We don't have access to the dissipation in the orthogonal, in the y direction, for example. So we don't have access to all the dissipation, but we have a very good agreement by this measurement. Very good agreement for low amplitude. If we take into account only the forcing frequencies, we have the blue curve, and this we take into account the forcing frequencies and some other frequencies, and we get better estimate, but we still have some dissipation that is missing. And part of this dissipation that is missing is that we didn't take into account, for example, mixing. Not everything that is missing here is mixing, but part of it is due to mixing. So at higher amplitude, we have non-linearities and some mixing. I will not explain all the factors that can explain that we don't have exactly a good agreement, why we are missing, but I just wanted to point out that mixing is a part where we inject energy, and part of it has been used to create this change of the background density that is mixing. And this is the final part I want to discuss today, a quantification of mixing. You will have 2 lectures by Philippe on this mixing, but I just want to explain how we can have access to a nice experimental technique to give you access to a quantification of mixing. To show you why I said that we have mixing at high amplitude, so I just come back to this movie. So we still have this attractor, we still have this shape that you will see, and then we decided to have huge amplitude of forcing. So we strongly increase the amplitude of forcing. You can still see the pattern of the attractor, but you can see already strong motion everywhere else. Usually you do this at the end of the day because your stratification is destroyed and you cannot use it anymore. So you fill the tank out and you need to do a new stratification. And you see that the dye now is diffused everywhere, and you can see here that you have some breaking of waves, and you can see some mixing in many parts of the tank. And that's why I said that high amplitude, part of the energy that's injected is transferred into a modification of the potential energy of the background, and this is mixing. And here you can see that if you are able to look at the density feed here using this dye, you can see some of the wave breaking. And this is the experimental technique I want to describe for the last part of my lecture, how we'll do this technique to measure the density during the mixing. I'll just make here. Sorry. And this is some mixing due to wave breaking. So the quantification, the experimental technique I want to describe, it's and you will see, it is important to quantify mixing it is important to measure rho prime and V. So the perturbation, the perturbed density field and the velocity field at the same location and at the same time. And this is rho prime. So V is measured using PIV, and rho prime, a technique that can measure it is what is called planar laser induced fluorescence. So the dynamics is 2D at the beginning. When you have strong motion like that, it's not clear the dynamics stays in 2D. So you can have also creation of 3D waves in 3D. So the third dimension cannot be neglected anymore. And when you have mixing, it's usually at very small scales. So you cannot say anymore it's in 2D. So that's, we see some mixing in the wave breaking, but still it can be, the mixing occurs in 3D. So it's, okay. So the idea now is to explain what is the principle of this technique of leaf. So PIV, I have just said, we use seeded particles, and for leaf, the stratified fluid is seeded with a fluorescent dye. And more precisely, we have a stratification in density Z, and the technique, let's say, all this technique I will describe is in a paper we have published in Experiments with Field, it's Tossman in 2016. And we do, again, a stratification in density. We do as well a stratification in dye. is the concentration of dye depends on Z and is proportional to the stratification in density. And why do we use a fluorescent dye? This is because of this principle. So the dye here, it's called of it's a dye which is called rhodamine. You have absorption of the dye at a wavelength, and it was the wavelength used by the laser for PIV. So the laser was a green laser at 532 nanometer. So you have absorption at lambda absorption, and the dye will re-emit some light at a different wavelength. Emission, re-emit light at lambda fluo, which is different at lambda abs. It's what is shown in this figure. So what you have is you have access to, so you prepare your stratified fluid, you add a stratification in dye, you have particles for PIV, you use a laser sheet at 532 nanometer, the dye will emit light at another wavelength. And more precisely, the re-emitted light, the light intensity that is re-emitted, so emitted by the dye, more precisely, is F is proportional to the intensity received by the dye. You have some saturation times C, and also C, and it's what is shown here, cannot be too large. And if C is too large, you are not linear using this law. So by measuring the intensity of the dye, of the light emitted by the dye, you can measure C. And this used this sketch, one of the last sketch I will show. Okay, so you have your laser, you use an oscillating mirror to have a laser sheet, and you have the what you observe. And then you need to use two cameras with two different optical filters. One is dedicated for PIV, so you have an optical filter that will remove the light. Basically, what you need, you have an optical filter here. This is for PIV. And in the other one, you have an optical filter here, which is for LIF. So each camera will be dedicated to one part. One is for PIV, one is for laser-induced fluorescence. Okay. So that's the first step. So I discussed this at the end because it's not an easy technique. Because you want not to have the light that is emitted by the dye, which is not related to the velocity field. So you really want the dye only that comes from the particles and not the light emitted by the dye. So that's why you need to separate the two patterns. The the light from the particles, if you have the pattern, you will look at the pattern. This is true, but when I said I need an optical filter for PIV, when you do the experiments, you have dye and particles. So if you use the laser sheet, the particles will diffuse light at 532 nanometer, and the dye will diffuse light at this frequency. So the camera, if you don't have optical filter, will see light emitted from the particle that is PIV and light that is emitted by the dye, and both does not give the same quantity. So you need to separate both to have on one camera the velocity, on the other camera the concentration of the dye, and if you have the concentration of the dye, you have the density. And then I will not enter in all the details. The image I show here, it's a raw image of the of F. And the problem, you see that the intensity becomes smaller, smaller, and smaller if the laser comes in this direction. This is because the light is because of absorption. So at each step, you have absorption. So that's why the emission is smaller and smaller and smaller and smaller and smaller. You have the problem of absorption. It's both a problem on what you want to measure, so it's a compromise. Because you have this problem of absorption, this technique, you need to have a huge post-processing method to remove the absorption. It's also necessary to remove the non-homogeneity of I. I means the intensity that is received by the dye. So you need to have a strong post-processing method to remove these two problems. So there are different techniques to do that. To remove the non-homogeneity of I, this is why we use first an oscillating mirror. And the second one is that we use a fluid where the index of refraction has been matched and is the same everywhere in the tank using ethanol. So this is to remove the non-homogeneity of the intensity, and to remove the absorption, at each step, we know what the concentration of dye here in this side. We know the trajectory of a ray, and at each step we compute this concentration of dye, knowing the concentration at before, and we do step by step to get the complete intensity emitted by the dye, and to have the complete concentration of dye in the tank. So that's when I say that it seems complicated, it's not easy to do. You need to be very careful to do this post-processing correctly. So that's why this method is not so easy to implement. So I will not go to the detail, but after the post-treatment, if it's done carefully, you obtain these results. So after the post-treatment, you get these results. It's exactly the same image, but here you have the density field. And here you have some line, some isopycnol. It's just sometimes it's easier for visualization to have it. So using this post-processing method, I didn't enter into all the details of the post-processing, but it's possible to do it. We can remove the absorption and obtain this density field. And as I said, and I will finish by this movie, we use laser-induced fluorescence to get the density field. We use PIV to get the velocity field. You have two cameras, they are synchronized. They are looking at the same field. The field of view is the same for the two cameras. And what you see, the movie is not working. Sorry. The movie was supposed to work. Okay. It's working on my computer, it's not working here. So I'm sorry, but you can see it. So the idea of this movie was to show you both the and the solution. Okay. Maybe you can see now the movie I want to show. You can see on the line motion of an internal wave, which is an internal wave mode, the arrow or the velocity field, and you have both at the same time at the same position, and you can see the wave breaking. And having both at the same time will lead to a quantification of the mixing that is occurring in the tank. And this will be the topics of the talks of Filippo. And I wanted to finish, so it's an experiment that is not easy to perform, having both at the same time, the same location, but I really wanted to finish that by this movie that is very beautiful. And this breaking is really related to the breaking of waves that you have in the surface along a slope. And I will end my lecture by this movie. So thank you for listening. If you have any question on this part, the last part is very difficult, is not easy to implement, so that's why we don't do it every day. And so the kinetic energy, I think, is this one. You are fully right. This is, in fact, this is a very good question, and it's very nice to have seen this. This is if the way the internal wave attractor is formed. So you have reflection. Here you have focalization. The focalization of, and you have smaller wavelengths, and you also have the density of energy that is larger after reflection. So here the energy is larger than this. So you have reflection, you have the wavelength that is smaller. So that's why this one is smaller than this one, and the kinetic energy here is smaller, is larger. So conservation of energy, since it's smaller, you have more energy here than here. Then the internal wave, the energy is going into that direction. And now you have dissipation. So because of dissipation, the energy becomes smaller and smaller and smaller. And also the widths become larger and larger because of the dissipation. We have measured that experimentally, and it's coherent it's compatible with just an approach where the thickness increases with viscosity. I think it's coefficient 1/3, something like that, and the energy is smaller. And so it is just because of viscosity due to the propagation and because of the reflection also. And here the energy becomes larger because of the focalization due to the reflection on the slope. Is there any other question?
Yeah, if there are no other questions, thank you very much, Silva, for a very nice set of 2 lectures.
Thanks.
I'm sure it's also going to be useful since we are putting it up on a link. There will be a lot more people who will view it. And already quite a few students have indicated, yeah, they've really appreciated experiments a little more after listening to you. Thank you very much.
Thanks.
Thank you,
Experiments are
Shobha.
always beautiful.
Okay, if there are no other questions, we shall continue tomorrow at 1:30 p.m. Indian time.
I will put my notes on the